Okay, good morning. First, I did want to give a shout out again to the sponsors and the organizers. I really enjoy this conference. I tend to think of myself as a very technical person, and there's a lot of great technical content within this conference. The other thing, I probably should apologize at the beginning. You might get a little whiplash in a couple places from what I'm about to present. I got put into the simulation, software simulation, hardware simulation area. I kind of noticed on the whole set of presentations, and that's normally what I've talked about in the past when I've been here, but this time, as you can see, I'm actually talking about, and I know it's the flight software workshop, but I'm actually going to talk a little bit about ground software. So with that, see if I can. Again, a little more whiplash. You know, I was going to go back to who we are, what our group is that actually did the development of SDF-1 and the ground software. So we work for NASA. I think everybody's familiar with that. We're at the NASA software IV&V program where we do software independent verification and validation, primarily for NASA, but also for a few other missions, some NOAA missions as well, some closely related things. We've been ensuring primarily NASA Class A mission success since 1993. So we're talking anything manned. IV&V's been done on ISS shuttle when it was around. It's on all the parts of HEO now. And then also, in addition to that, all the really high dollar NASA missions, James Webb, Parker Solar Probe, those types of missions. The facility and the people there do full development life cycle software, requirements, design code, test, etc. I put and related system because in this type of industry, there's no way you can look at software without really thinking about the whole system. I think our keynote speaker mentioned that this morning. And then so within that, I actually work on a team called the JSTAR ITC team. And those two terms are sometimes used interchangeably, which is a little confusing. But essentially, the independent test capability team, we provide the personnel for the JSTAR lab to actually develop simulations. And that's what ends up getting used by the other people at IV&V to actually do their job, to do testing with often the actual flight binaries. We do a lot of instruction set simulation and that sort of thing. We also have done emulation, flight peripherals, buses. We just heard a talk about QEMU. We've done a lot of stuff in CIMIX in the past. We're doing some things now in QEMU as that's becoming a big viable platform for us. And we do a lot more. So the basic thing our group tends to do is take the whole system and the satellite and put it on a laptop. So that's kind of the generic. So now back to the whiplash again. So what I was going to talk about though is the actual mission ops stuff we did for our CubeSat simulation of Flight 1. So this was a 3U CubeSat. The primary objective for our group in particular was to develop the NOS Cube simulator. And I think that's been presented several times at the workshop in the past. And so that's kind of the tie-in with our day jobs, with our big simulation type work. We did have 4 science payloads and built by different departments at West Virginia University. And so we actually finally launched last year, about within a couple days of now. And on the 19th of December last year, we actually finally made our first contact, which was great. And we'd worked hard to get to that point. But the question is, now what? How do we actually efficiently and effectively operate? I mean, we were trying to develop the simulator, but now we actually have science payloads, and we have to actually work with all that and do operations. So it's not like we didn't have anything to begin with. We already were using Ball Aerospace Cosmos, as was mentioned earlier this morning. We were doing testing with this in our lab. We did development of all the command and telemetry tables. That part was already there. We already knew how we were going to hook up to Wallops to actually do the commanding through the entire comm chain. So that part was all there. So we could actually operate the satellite, on a day-to-day basis, send commands up, get data down. So what didn't we have, and what kind of things did we want to add then? So as I mentioned, we're using a UHF antenna down at Wallops. It's a shared resource. We're not the only user of it. There's about a dozen CubeSats, I believe, using it. And so since it's a shared resource, they provide a schedule weekly of who gets time when. So just because we're in view of the antenna doesn't mean we get time. So we have to work through that. And then basically they come out with a spreadsheet that says when we get our time to talk. So then the other thing that we did was I kind of wanted to say, okay, well, what's that look like on a day-to-day basis and even on out days? So we came up with this homegrown tool called the Orbit InView and Power Planning tool. It's actually part of NOS-Cubed. It's kind of a little piece off in the corner from the main purpose of NOS-Cubed. But the idea was to generate kind of a visual view of what a schedule would look like. And so what's shown, and it's not real readable, but I'll just try to describe it. The green line represents one single day. So that's the current day. And then below that, down here, the yellow and black are indications of when we're in sun, when we're in umbra. There's actually small penumbra pieces there. So that's all based just on two-line element sets and propagating the two-line element sets. So we have that available. What was more interesting and useful for our use case is that on the lines above, we have two different antennas, and the one on the top here is actually for the Wallops UHF antenna location. And so we've indicated with little bars when we're going to actually be in view of Wallops. And then beyond that, once we actually understood what the spreadsheet format was going to look like, we're doing some automated parsing of the spreadsheet. And so we can indicate with different colors. So the purple color indicates that we're in view of Wallops, but we don't have a contact planned. Or the blue indicates we're in view of Wallops, and that's when they've actually assigned us time so that we can actually take a pass. And so we build up this capability, and this allows you to kind of look forward and say, okay, when are we going to have operators needed? You know, and there's not a very large group of operators, one or two. And what time are the passes going to be? You know, it's a low Earth orbit, 80-some degrees. It's not sun synchronous or anything, so these times tend to wander, you know, as the days march on. So then beyond that, that kind of helps you with understand what's going to happen tomorrow or the next day or even today. But we put together some things to actually help the operator on the current pass. So what we put together was an azimuth elevation range table. So on the left is a table, and it's just a typical ephemeris type table, time, you know, every 15 seconds or so, azimuth elevation range. But then what we also did was we created this bullseye looking graph to display what the track's going to look like as the antenna's tracking the satellite across the sky. And so the way to read this is the horizon is the red line, okay, and zenith straight up is the very center. So it gives you an idea of your elevation. You're going up in elevation as you get closer to the center. And it also gives you an idea of azimuth. And I like to tell people, I'm used to reading maps. It's backwards from a map since it's a sky chart. So west is on the right and east is on the left. So you can get an indication of how the antenna track is going to look whenever it's actually in contact. And then what we've done is overlay in black the track as the antenna would follow it. So why? Why would you do this? Well, I mean, you've got typically times when you're going to have better comms and worse comms. You know, when you're at a very low elevation angle, you're going further, you're going through more atmosphere, your link maybe not close. So it kind of gives you an indication of, you know, where you are in terms of that. We also had some things we put in. We had a known RF interference source, so we colored that in red. It gives the operator kind of a visual idea as they're taking a pass, you know, of what's going on. And so I think Matt eventually, he used this, but also just his own notes, gradually got to understand better and better when he would have good comms and when he wouldn't. So that was for the pass support stuff. So then that's kind of all on the planning side and operations side. What about post-pass type information? So in terms of that, what we ended up doing was we took the same chart that I just showed on the last page, and we overlaid it. And so what we overlaid it with was we actually knew when we sent the commands, and then we would have times from when we actually received telemetry. And so we were able to overlay the track, the black track, with colored dots to indicate some of this information. So typically when we would start a pass, and these are time tagged as well also, so you can kind of figure out, are we going north to south or south to north? So we typically send a test command at the beginning, so we have a clear data test command. And then every time we have a blue one here, that's an indication that we sent up a command to ask for data back. So we're pulling data from the satellite, our telemetry that's been stored on board. And then when you see the orange ones, those are commands just to do something. Power on some switches, power on an experiment, that sort of thing. So we don't expect any response back. We're just sending a no response expected command. And then the other interesting thing is when we get the telemetry back, then in the green we've coded when we actually had a receipt of telemetry. And so you can see in some cases, you know, we sent up a command, asked for data, got telemetry back, asked for data, got telemetry back, asked for data, okay, you know, this apparently we weren't in a good communication geometry, we don't have any attitude control, so we're tumbling. We have a relatively omnidirectional antenna, but it's not, you know, perfect. And so, you know, in these cases, there's some Doppler shift stuff that has to happen that we've worked out with the ground station. You know, so there was no telemetry received here. So it kind of gives you a graphical feel after the pass of what happened. And then the other thing we did was we actually automated this very simply with cron and at to run a few minutes after every pass, generate this data. And so we would generate the plot and then send it out to the team on Slack, so that really there was nothing anybody had to do. This information just automatically gets pushed to us. And in addition, what we did was we strip off a couple lines from some of our key telemetry points and put them out on Slack as well. And so one of the key telemetry points we look at is what's the main bus voltage of the spacecraft. And so all this gets pushed out, and so, you know, every day I can just look, or if Matt can after the pass, what's going on. So what else? What else did we have to automate? Okay, like I said, we actually have 4 science payloads on board. We're getting housekeeping telemetry down. All this is coming down in a binary format, and as it is, we don't want to send off the binary to the scientists. We want to actually give them textual versions of that. And so what we've done is set up just, again, automated jobs to post-process the pass and then generate comma-separated value spreadsheets for them of time-tagged data from their experiment and time-tagged data for all our housekeeping and so on. And then in order to automate it even further, we're sharing this. We wanted a way to automatically share this out to them. Like I said, they're not all co-located with us, so we couldn't just put it on a server, you know, at the facility. So we're sharing it out to a Google Drive share so that they can actually get access to it. And then the final thing, this was one of the last things we kind of added in, was they would ask me, when did you run my experiment? When did you get data back from my experiment? And I said, well, okay, so I can look through the directory structure. And, well, it's a little cumbersome, so I wrote a script and then actually generated block type calendar views. And so on the block type calendar views, and I know it's not readable, but indicating when an experiment was run, what day it was run on, and then what day we got data back from it. So that kind of gives you an at-a-glance view, and so then you know where to look. So we're saving things off into a day-by-day directory structure, what days to look at for data for your science experiment. So again, like I said, all this was automated as well. And why? Well, kind of going back to the beginning, this is not really our main job. We tend to do simulators. We do development. We're not an operations group, nothing like that. So the idea was to offload all the things that we could. And so basically when we take a pass, our operator, Matt, or myself, or whoever else, I mean, you just need to take the pass, you know, spend 15 minutes or half an hour, and that's it. You know, everything else has been automated so that we don't have to do the rest of this work. And so now a little whiplash again. So now we go back. I told you who we are, so now a little bit more about what we do. So of course, as I've been talking pretty much the whole presentation, we did SDF1. We typically do software-only simulation. And as I said, for the Class A type NASA missions, so we did NOS cubed as a companion to SDF1, so you can do small satellite simulation. And then we've done simulators for human exploration, where for SLS we've taken the Artemis and Maestro that was talked about earlier, condensed it down onto a laptop, totally software-only sim. Like I said, again, the focus at IV&V is really on software IV&V. You know, so that's really the part we're really looking at. So we want the software part, not so much, you know, you recognize hardware is important, you're going to have to do hardware testing, but we're primarily looking at software. So we do software-only sim for that to high fidelities. And then we've brought in the exploration ground systems code and created a sim called GS2. And we've brought in Socrates from Lockheed Martin for the MPCV Orion. So we're putting together an entire HEO mission sim. And then we've also done sims for other science missions, such as James Webb Space Telescope. And again, we've condensed it all down into one virtual machine rather than racks and racks, you know, that you would typically have. Working on the same kind of thing for WFIRST. We have a new simulator we're working on called WISP. And then are eventually going to do one for Europa and Psyche missions as well, because those are very high dollar, very important missions to NASA, and ones that the IV&V program has decided need IV&V, and we're going to work on. So with that, I'll wrap up and say thank you very much, and put a couple of links down here for myself, but then if you want to know more about IV&V or the JSTAR team within that, and then some links about SDF1 and NOS cubed. And finally, I'll leave you with a couple of pictures. The camera was almost an afterthought on this because we're really not using it for a science experiment, but we do have one on board and we occasionally take pictures. And these are the two of the pictures we've taken. Again, they're very surreptitious because, as I said, we have no attitude control. Snap the picture and we'll find out what we get. And so these are two of the nice ones that we've got. So with that, thank you very much.
Thank you, Mark. Any questions? Nope, guess not. Thank you. So we have a couple minutes. We're going to do a raffle, so get your raffle tickets out.